Great. So thank you everyone for joining us for this AMI seminar this week. We have Yuhe Zhang giving a talk on deep learning and X-ray image reconstruction. She's a researcher at Lund University in Sweden. Thank you for being here, Yuhe. Take it away.
Okay, thank you very much for the introduction, and thank you very much for inviting me to give this talk. So it's really a great opportunity for me to present my research here. So the topic of my presentation today is physics-inspired deep learning for X-ray image reconstruction at high-brilliance sources. And yeah, I'm Yuhe Zhang. I'm at synchrotron radiation research at Lund University. I will start with a brief introduction about my academic journey. So I did my bachelor study at Fudan University in Shanghai, focusing on physics. And during the last year of my bachelor study, I had the opportunity to visit Lund University as an exchange student. So that's how I moved to Lund. And then I did my master's at Lund University and also my PhD here. And regarding the research, before my PhD, my bachelor and my master's project focused on atomic and molecular spectroscopy. So in particular, I work on flame temperature measurement using fluorescence and emission spectroscopy. So I just put a small example here. So as you can see in this animation, we want to study the flame temperature using the different emission lines from these alkaline metals. After my master's study, I found myself interested in deep learning and also imaging science. And here at Lund, we are very close to Max 4, which is the first generation synchrotron radiation source in the world. So it's quite natural for me to move to X-ray imaging and start my PhD there. My PhD project is about advancing X-ray imaging with deep learning. Most of the projects that I will present today are from my PhD work, as you will see later. And I'm currently at a transition state. So I'm doing my postdoc here in Lund, working on 4D X-ray microscopy and deep learning for medical imaging. And after this summer, I moved to Stanford, starting a new postdoc there, working on physics-informed AI. I'm very looking forward to that. And as I mentioned, most of the projects I will present today are from my PhD work, so I will just briefly introduce who are we. This is a photo of our group. We are the X-ray imaging group at Synchrotron Radiation Research, Lund University, under the lead of Associate Professor Pablo Vaniniva Paris, who is the handsome guy in the middle. And this is a map showing where we locate. So as you can see, the black dot here is Copenhagen. I can maybe turn on the data point. So here's Copenhagen and Lund is here. It's actually just 1 hour away from Copenhagen, so it's very close, but we're located in Sweden. And in Lund, we have the Swedish National Lab Max 4, which is the first generation synchrotron radiation source in the world. Our lab works on pushing the limit of state-of-the-art time-resolved 3D imaging. And in particular, we work on a technique called X-ray multi-projection imaging. In our group, we have people working on both the experimental setup part and the data analysis and reconstruction part of this technique. And me, myself, I'm working mainly on the AI reconstruction algorithm part. During my PhD, I focused on applying deep learning to address real experimental challenges in X-ray imaging. For example, in 2D, we work on the problem of phase reconstruction and flat field reconstruction and flat field correction. And for 3D and 4D, we focused on sparse field reconstruction problems. In most of the projects, we include the physics of X-ray imaging into the learning process. And we demonstrate that deep learning plus physics can serve as an enabling tool for X-ray imaging, unlocking possibilities that were not possible before. In this presentation, I will cover all these techniques. I will first introduce the 2D method for flat field correction and phase reconstruction. And after that, I will focus on 3D and 4D reconstruction approaches. So that's a brief introduction, and let's get started. I'll start with FFCGAN. It's flat field correction GAN. It's a deep learning approach for shot-to-shot flat field correction at X-ray free-electron lasers. The result of this approach is published on this paper. And I will first show an example of flat field noise. So this is the raw detector frame recorded using the megahertz imaging system at European X-Ray. There's no sample in this movie, it is just illumination. As we can see that there are drift in the illumination that changes from shot to shot. The flat field noise will certainly affect the quality of the imaging system. And if we separate different components of a detector image, as shown here in the simulation, it contains three parts: the flat field, the noise-free image, and the dark current. The flat field is determined by the illumination and the detector systems. The noise-free image is what we want to measure, but the dark current usually comes from the home noise of the detector. The goal of flat field correction is to get a noise-free image of the object from the noisy detector frames. It might be intuitive to think that an object image can be obtained by subtracting the dark current from the image and then divided by the flat field. And this is the conventional flat field correction method. Unfortunately, it is only valid for slow variation imaging systems, but not for X-ray free-electron lasers. As I showed in the previous movie, that at free electron lasers, illumination changes very fast in megahertz rate. Dynamic flat field correction can be applied for such scenarios. It is based on principal component analysis, which estimates the flat field component of each image and correct it accordingly. Dynamic flat field correction method works for fast variation imaging systems. However, this approach is slow and cannot correct feature shift because it is a local approach. Usually, during the experiment, it is necessary to collect flat field before and after each experiment, which consumes both time and data. To solve this problem, we propose deep learning FFC method. This is an end-to-end method which learns the noise-free object from the detector frame. And it is trained on dynamic flat field corrected dataset. After the training, it offers fast, nearly real-time corrections. And this is a non-local approach because it is based on convolutional neural networks. This is how it works. So FFCGAN is a supervised learning approach, meaning that we have a ground truth or an oracle to get this learning approach. And we input the noisy data into a generator, which is a convolutional neural network, and it outputs a prediction. We can train the network by minimizing L2 loss. And these are typical steps for supervised learning. On top of that, we introduced a novel loss function based on Fourier ring correlation. We perform Fourier transform on the images and minimize the correlation of the frequency space images over the rings. This Fourier ring correlation loss will force the network to learn all frequencies equally, which is especially important for capturing high frequency details. And this method has been proved to be quite effective, not only in our paper, but also in some other publications. And in addition, we ask the network to learn from other noise-free images. This is done by a discriminator. The discriminator sees both the noise-free images and our predictions, and teaches the generator to generate images that follows the distribution of the noise-free image. And the combination of the generator and the discriminator is a generative adversarial neural network, or GAN for short. That's why it is called flat field correction GAN. So here are some results. We have the raw detector frames and the result from the three FFC method. If we zoom into the small area as marked in the red box here, we can see some strips in the raw detector frame. The conventional flat field correction method fails to suppress these artifacts, but both dynamic flat field correction and deep learning flat field correction method successfully removes them. We also calculated the modulus of the gradient for the marked area over 1024 images, and the average results are shown here. As we can see that both the last two methods, the dynamic flat field correction method and the deep learning method, outperforms conventional flat field correction. And on top of that, deep learning method is 10,000 times faster than the dynamic flat field correction, offering the possibility for online analysis. So that's it for the FFCGAN part. It is a supervised learning approach, and this is the only supervised learning approach that I will present today. And I will now move on to PhaseGAN, a deep learning phase retrieval approach for unpaired dataset. The result of this approach are published in these two papers. As we know that when X-rays pass through a medium, they undergo changes not only in amplitude, but also in phase. The attenuation of the amplitude is related to the imaginary part of the complex refractive index, which is the beta here. And the phase shift is related to the real part of the complex refractive index, delta. Absorption contrast imaging is widely used today because it is easy to measure. However, directly measuring the phase shift is challenging. Instead, the phase shift is typically determined by solving the phase problem. The phase problem is a fundamental problem in X-ray imaging. And this is an example of a phase contrast imaging experiment. The X-ray beams come from the left, illuminate on the sample, and the diffraction patterns can be recorded on the detector. If we move the sample towards the detector, we can observe changes in the diffraction patterns as well as the magnification level. As we mentioned, the sample's properties are defined by its complex refractive index, which causes both attenuation and phase shift in the wave field. However, since the detector can only capture the intensity of the wave field, the phase information is lost. We need phase retrieval algorithms to reconstruct phase from the intensity measurement. There are several ways to solve the phase problem. The first is analytical approach. These approaches are fast, but they rely on certain assumptions. When the assumptions does not hold, they are prone to artifacts. The second are iterative approaches. Iterative approaches map between the object space and the detector space using a physical propagator H and apply constraints on both space. In the near field, the propagator is the Fresnel propagator, while in the far field, it's a Fourier transform or a Fraunhofer propagator. Iterative approach they rely on basic assumptions of wave propagation and interaction with matter and provide a general solution to the phase problem. However, these methods are slow and the convergence is not always guaranteed. We might want to have a dream solution that is fast, general, artifact-free, and offer good convergence. And this brings us to PhaseGAN, our deep learning solution that combines physics with AI. PhaseGAN is an unsupervised approach, meaning that there's no need for a paired training dataset. By the time I started this project, deep learning phase retrieval approaches are mainly supervised, requiring paired training dataset. That means we need to dephase each of the hologram intensity image to prepare a paired training dataset. This is not always possible. For example, it is not possible for low flux and low dose imaging experiment. Suppose we have a noisy and low contrast image like here that cannot be reconstructed using conventional phase retrieval method. How can we prepare a paired training dataset? Well, for that, we can use unpaired approach, unsupervised approach. We can prepare unpaired dataset that combine these hologram images with the ground truth prepared from a completely different imaging modality. It can be recorded using a different imaging method, such as histology or radiography, or using the same method, but with completely different imaging conditions. The use of unpaired dataset enables possibilities when prior phase reconstructions are unavailable. So PhaseGAN is based on CycleGAN, which is an unsupervised deep learning model that learns the image translation between two spaces using two-generator neural network. And as shown here, the detector generator GD and the object generator GO. And two discriminators are applied in both spaces as constraints. CycleGAN learns a pair of cycle consistency functions, meaning that if we map an image from the object space to the detector space, and then map back to the object space, we should end up at exactly the same image. In PhaseGAN, we include the physics of X-ray propagation by introducing the physical propagator H. And the physical propagator here is the same as the one used in iterative approaches. So in the near field, it's a Fresnel propagator, and in the far field, it's a Fraunhofer propagator. Because of the inclusion of the physical propagator, our detector generator, GD, does not need to learn the well-known physics of image formation, and it can only learn experimental effects, such as flat field noise and point spread function. And as FFCGAN, we also introduced the loss function based on Fourier ring correlation. and to enhance the performance of our approach. We validated the performance of PhaseGAN using simulated holographic images, and this data are from the SELECT-A dataset. And here are the results. First, we have the ground truth. It is two-channel. We have both the phase and attenuation. We compare the ground truth to the reconstruction result of supervised learning and cycle-GAN, PhaseGAN, the two unsupervised learning approaches. It might be difficult to say the differences here. We calculate the mean square error over 1,000 images, and the mean value is reported here. As we can see that by including physics, PhaseGAN outperforms cycle-GAN and performs at the level of state-of-the-art supervised learning approaches. But remember that we cannot get paired training data sets from experiment, so we need to use unpaired approaches. We also applied PhaseGAN to explore the fast analysis, the fast process of cell rupture of metallic foam. This movie was recorded using single pulses of APS at 6.5 megahertz. And as we can see here, the temporal resolution of this image is about microsecond. So it is very fast acquisition, and the frames are too noisy to be reconstructed by classic phase retrieval method due to the fast acquisition. We managed to dephase and denoise using PhaseGAN. Here are the results. The reconstruction time is around 0.4 milliseconds per frame, making it possible for real-time and online data analysis. We also test the adaptability of PhaseGAN to non-perfect imaging systems. So here is the diffraction pattern of polystyrene macrosphere data affected by Gaussian blurring. The data is shared by these authors here. And we want to reconstruct phase and attenuation from this blurred image. And here are the results. We compare the results of PhaseGAN to cycle-GAN and the ground truth. If we zoom into a small area as marked by the red box, we can see the difference. We can see that by including physics, PhaseGAN outperforms cycle-GAN and generate more reliable results despite the influence of Gaussian blurring. So for a quick summary and outlook of PhaseGAN, it is developed to solve the challenge of phase retrieval for low flux and low dose imaging experiments. And our solution is combining physics with AI. PhaseGAN is an unsupervised or unpaired approach, meaning that there's no need for a paired training dataset. We include the physics of X-ray propagation into the neural network and also introduce a novel loss function based on fair reincarnation to improve the performance. As an outlook, PhaseGAN offers new possibility to explore low flux and low dose phase reconstructions, such as medical imaging and ultrafast imaging, where prior phase reconstructions are not available. And it also has the potential to be applied to non-perfect imaging systems. So that's all for the 2D part. I will now move on to higher dimensionalities, 3D and 4D. So I will discuss ONIX and 4D ONIX, our deep learning approach for 3D and 4D reconstruction from sparse X-ray projections. Speaking of 3D and 4D imaging with X-rays, traditionally, classically, 3D and 4D imaging with X-rays are performed using tomography. In 4D, it's time-resolved tomography, also called tomoscopy. In a tomography experiment, we need to record hundreds up to thousands of projections between 0 and 180 degrees. And this is usually done by rotating the sample. As we can see here, the rotation speed is around 0.3 Hertz. State-of-the-art tomography can capture dynamics up to 1 kilohertz. And this result is reported here in this paper in 2021. As you can imagine, this will require 500 rotations per second. It will introduce a strong centrifugal force to the sample. In fact, for 1 millimeter object, the centrifugal acceleration is around 500 times the gravitational acceleration. So it is quite significant. This is clearly not suitable for study fast and sensitive dynamics, for example, like fluid dynamics. And it is also not suitable for single shot approaches because we need to record multiple projections by rotating the sample. X-ray multi-projection imaging was proposed to solve this problem. In X-ray multi-projection imaging, the sample is fixed in the center without any scanning or rotation. Whereas X-ray beams is split, and we illuminate the sample simultaneously from different angles and records the projections using multiple detectors. This approach allows for 3D imaging without scanning the sample, so it is compatible with single-shot approaches because we don't need to rotate the sample. And it also allows for 4D fast dynamics without disruptive forces. We have performed several experiments of X-ray multi-projection imaging at different high-brilliance sources, as marked here. And here's an example of our XMPI setup at 4 max beamline at max 4 here in Lund, in Sweden. And as we can see here, the X-ray beam coming from the bottom right, and it hits 3 crystals. And the X-ray beam are diffracted into different angles upon reaching the crystal. And right before the sample, there's another crystal that is maybe not easy to identify, but it serves as a recombiner that recombines X-ray beam into the sample. So with this setup, we can record 3 projections simultaneously from 3 different angles. This is how it actually looks like in the experimental arch. So the blue curve, the blue line here shows the X-rays. And as we can see here, the X-ray beam is diffracted by the crystals, and then they illuminate the sample simultaneously from 3 different angles. And we use 3 high-speed cameras to record projections. The viewpoint of the 3 projections are recorded at 0 degree, 40 degree, and 52 degrees, respectively. With this setup, we can achieve a temporal resolution up to 10 kilohertz, and with a spatial resolution of around 8 micrometers. We also performed XMPI experiment at European X-Ray Free-Electron Laser. So this is an example of our experiment there. We split the beam into 2 directions and illuminate the sample simultaneously from 2 different angles. The sample we started was water droplet collision. At European EuXFEL, we can achieve temporal resolution up to megahertz. So here the temporal resolution is around 1.1 megahertz, and the spatial resolution is around 12.8 micrometer. And this is the results that we get from European EuXFEL. These movies are recorded using single pulses of European EuXFEL at 1.1 megahertz. And the angles between the 2 projections are 23.8 degrees. And as we can see, the collision of these 2 water droplets, they're merging together and they are moving down because of the gravity. From this data, we want to achieve a 4D reconstruction of the sample. But as you can imagine, this is very challenging because we only have 2 projections 23.8 degrees apart. The reconstruction task is very under constraint. How can we do that? And our solution is again to use physics plus AI. I will now explain you the key components for the ONIX, our deep learning model. And ONIX is for 3D reconstruction. So we use a neural network based on neural implicit representation to learn a continuous representation of the refractive index at each 3D or 4D coordinate. So for ONIX, it is a 3D reconstruction approach. We use 3D coordinate, and for the ONIX, it's 4D coordinate. So here, delta and beta are the complex refractive index, and also X is a spatial coordinate, T is a temporal coordinate, and N is a network. So imagine we have our object here. We can select a query point in 3D or 4D space, and our goal is to learn the refractive index of the index at each 4D coordinate. We can constrain the query point using the measured projections, similar to iterative 3D reconstruction approaches. So for example, if we have 2 projections measured from the experiment, then we can constrain with 2 projections. If we have more projections, then we can constrain it with more projections. So our approach is a self-supervised learning approach. It is minimized only on the sparsely recorded projections. No 3D ground truth or no 4D ground truth is used to supervise the learning. But how can we constrain the network? How can we constrain our model? We need to incorporate the physical model. As shown here, we can take many query points along a certain ray direction. And this will give us the refractive index along the ray. If we integrate the points along this ray direction, then we can get a pixel in the projection image. This integration is based on the law of X-ray propagation and interaction with matter. Here we use projection approximation, but it is also possible to incorporate the propagation model and extend it to phase contrast imaging or other imaging modalities. When we have enough query points, we can generate a predict image or a prediction. The prediction can be either a mirror view or a novel view. If it is a mirror view, then we can constrain it with the mirrored projections from experiment. How can we constrain the views, novel view that have not yet been mirrored? For that, we use a generative adversarial neural network, like we talked before. As shown here, we introduce a discriminator neural network. The discriminator sees both the prediction and also the real projections from the experiment. And it teaches the generator to generate predictions, follows the distribution of real experimental collected projections. And we need to mention that the discriminator sees not only just 2 projections from a single time point, but the projections over all experiments and samples. We measure multiple experiments of similar samples, and our algorithm allows to transfer knowledge across different but similar experiments and samples. It is similar to what is done in cryo-electron microscopy. So let's now look at some of the results. First, I will show some 3D reconstruction results from ONIX. And this image shows 8 collected projections from Tomcat beamline at Swiss light source at Porsche Institute in Switzerland. It shows metallic forms. And we collect in total 96 projections, but we only use these 8 projections to validate our method. And our goal is to reconstruct 3D from only 8 projections. We reconstruct 3D using 3 different methods. So first, it's SART, or simultaneous algebraic reconstruction technique, which is a standard sparse wave reconstruction method for sparse wave reconstruction problem. We have it for reference. And also the ground truth here is prepared using 100 projections. And also we have the result from 3D supervised learning approach. It is trained with paired dataset. In this approach, we train each slice individually, and we have the ground truth as the supervision. And then we have the result from ONIX, our unsupervised learning approach that says nothing more than the 8 projections. So that was a slice, and here we have the 3D movie. I can play it. So this is how it looks in 3D. So the sample is being rotated in this rendering. As we can see that SART fails to reconstruct the 3D because the problem is very ill-defined. We only have 8 projections. 3D supervised learning reconstructs the shape of the metallic form, but it has some problem with stacking because it is trained on individual 2D slices to fit into the memory. And ONIX, our unsupervised approach, it says nothing more than 8 projections, but reconstruct quite decent the shape of the structure of the metallic form. And also I need to mention that since we don't have the ground truth, then 3D supervised learning approach is not suitable for our real experimental cases. So now I will show the 4D reconstruction result from 4D ONIX. So remember, this is our experimental data set. We have the projections recorded from 2 angles, 0 and 23.8 degree apart. And this is our reconstructions for ONIX, rendered from both the side view and the top view. We see the merging of these two water droplets, and they're moving. The result here were trained with only two experiments of water droplet collision, each with two projections with the same sample orientation. Unfortunately, we didn't have time to collect more experiments during the beam time, so we only have two experiments. We validated the performance of our approach using simulated data because we don't have experimental ground truth for this ill-defined problem. So we simulated 16 experiments of water droplet collation. This is done by our cooperator, Robert Clofton, using the software Lund. Each experiment contains 75 timestamps with varying droplet orientations. So we simulate different size, different orientation, and different collision velocities of the droplet according to the experimental uncertainties. And from these 16 simulations, we generate 2D projections based on our experiments at European X-Ray. As we can see here, we generate simulated projections at 0 and 23.8 degree, same as what we did in the experiment. And our goal is to reconstruct 4D from these two projections by combining different experiments. If we look at the frequency space, so in the Fourier space, if we have only one single experiment, then we only have two lines in the frequency space because we have two angles, 0 and 23.8 degree apart. But if we have more projection, okay. Sorry, can you hear me?
Yeah, we can hear you.
Okay, my laptop stuck somehow.
Yeah, we can see you and we see the same slides, but we can hear you and we can see you well.
Sorry, I think there's some. Okay, my laptop is out of power somehow. It's being charged. I don't know what happened, but maybe it's the connection. I'm really sorry for that. I just no, it's still stuck. All right, I guess I might need to restart the computer. It's starting.
Okay. Okay, we'll take a quick intermission. Okay, now we're back. Yuhe, continue, please. Thank you.
Okay, I'm really sorry for the disruption. So I will just continue from where we ended. So we simulate 16 experiments of water droplet collision, and from this we get two projections according to the experimental setup at European X-Ray. And we want to reconstruct 4D from these two projections. So if we look at the Fourier space, with single experiment, we only have two lines in the frequency space because we only have two projections, like two angles, 23.8 degree apart. But when we include more experiments, then we can have more information in the frequency space. So you can see here we have more angles, more lines here. And here is our reconstruction from the two projections. First, we have the ground truth rendered from the side view and top view. And we have the reconstruction, the 4D reconstruction from single experiment, 4 experiment, and 16 experiment. So I will now play these movies, and you can see how it goes. Yeah. So we can see the collision of this water droplet. They merge together and becoming like this disco-sized shape. And we also calculate some statistics. As you can see that with one single experiment, the performance is not that good, but with 16 experiments, we can get quite decent reconstructions with a resolution of around 4 voxels, meaning that we can get better results by minimizing over more experiments. And we also validate our approach using experimental time-resolved tomography data of additive manufacturing. And this experiment was conducted at the Tomcat beamline at Swiss light source at Porsche Institute in Switzerland. It captures the Melput dynamics of magnetite modified alumina. The experiment was performed at 50 Hz, and in total 200 projections was reported within 180 degrees for each tomogram. For each time point, we select 3 projections out of 200, as shown here. So each column shows the 3 projections for a single timestamp, or a single time point. And the 3 projections are corresponding to 0 degree, 27 degree, and 54 degree. Here we use the blue boxes to mark the melting region, so where the dynamics happen. So you can see the difference in the projections. And as we mentioned that the power of the ONIX is combining multiple experiments and minimizing the difference among experiments and samples. But how many experiments are needed? We evaluate the performance of the ONIX as a function of the number of experiments. And this figure shows the performance plot across all time points for the mean squared error and also the structure similarity. So they are both the lower the better. And as we can see here, the performance improves quite a lot with the number of experiments. And with around 16 or 32 experiments, the results are already quite good. So here we show the 4D reconstructions. First, we have the ground truth reconstructed using all 200 projections. And we have the result from 4D ONIX reconstruct by combining 3 projections of 32 experiments. And for reference, we also compared with 2 other methods. First, it's SART, like we mentioned before. It's an algebraic reconstruction technique that works quite well for sparse wave reconstruction. And we use 24 projections. This is the minimum amount of projections that we can have to make it look good. And also we compared with noise to inverse, as shown in this paper at the bottom left corner. It is a state-of-the-art self-supervised learning approach. It's another deep learning approach, and we also use 24 projections. We can see here the reconstruction of noise to inverse has some problem with the edges because of the noisy of the detector frame. And I will now play the video so you can see the melting process. We can see that there are some imperfections in the 4D ONIX reconstructions. Some of the static features were not fully reconstructed. And one of the notable example is the bottom right tip as marked by the red circle. But this comparison demonstrates that 4D ONIX, when trained with 32 experiments of 3 projections, achieve performance levels compared to SAT and noise to inverse when they are trained on single experiment with 24 projections. But so far, experimentally, we cannot get 24 projections simultaneously. So we have to use 3 projections, unfortunately. So here's the short summary and outlook for the ONIX and ONIX. They are developed to solve the challenge of reconstructing 3D and 4D from ultra-sparse projections as measured by X-ray multi-projection imaging, typically no more than 5 projections. And our solution is to combine the physics of X-ray imaging with AI. And ONIX and 4D ONIX learns functional dependence of the reflective index at each 4D or 3D coordinate. It is a self-supervised learning approach trained only on 2D projections, no 3D or 4D reference. And we incorporate the physics of X-ray render or X-ray imaging into the neural network. And as inspired by cryo-electron microscopy, we measure multiple similar samples and minimize over all experiments and samples. So as an outlook, our approach offers directly 3D 4D reconstruction from as few as 2 projections. And when combined with X-ray multi-projection imaging, they allow us to capture dynamics up to 1,000 times faster than the current tomography. That is megahertz rate. And this opens new frontiers for time-resolved X-ray imaging, opening new possibilities for scientific and industrial studies, especially for sensitive dynamics such as fluid dynamics. So that's all for my talk, and I would like to acknowledge my supervisors and our cooperators for this, to make these projects happen. I'm really sorry for the laptop issue that happened. That's all. Thank you very much for today.
That's great.